Let's just get to the point. Why do we learn differential equations? Because they are the equations that describe how nature works. The universe one day said, boom, here's a bunch of stuff, and then we said, cool, how does this all work? And then the universe answered, differential equations. Differential equations are used in various phenomena, from modeling population growth and electrical circuits to simulating chemical reactions. Differential equations play a vital role. One fascinating example is mixture flow problems, where we analyze the concentration of substances in mixtures. Now join us as we uncover the dynamic world of differential equations and their practical applications.
A mixture flow problem involves modeling the rate at which substance like salt, sugar, or chemicals dissolves in or flows out of a container with a fluid, usually water. The concentration of the substance in the fluid changes over time due to this inflow and outflow.
The first thing that we're going to learn here is in terms of mixtures. The problem of mixtures in the application of the differential equations is that the rate of change of a substance in a volume is equal to the rate of entrance minus to the rate of exit. In mathematically, if we are going to put this into our differential equation, we have dx over dt is equal to r sub I times c sub I minus r sub o times c sub o, where our r sub I is the volumetric flow rate at the entrance, and our c sub I is the concentration of substance at the entrance. So, ang meaning din sa R sub I is how fast the liquid together with the solution is coming inside the tank, where the R sub O is the volumetric flow rate at the exit. So, it means the liquid has a rate of exit and a rate of entrance. And our C sub O is the concentration of substance at the exit. So, our C sub O here is usually not given in the given problem. So, we usually express as x over v. So our C sub O is expressing as x over v because it is usually not given in the given problem. And where x is the amount of salt at any time p, and the v is the final volume of the solution at any time p. So to find the value of v, or the final volume, is we use this equation, where v is equals to initial volume plus r sub I plus r sub O, where r sub I plus r sub O are both multiplying by their time. So we're going to illustrate for better understanding the concept now. So we have here a tank or container, and the concentration of the substance inside the container, which we denote as dx over dt, is equal to the rate of entrance, or the input rate, minus to the rate of exit, or the output rate, where both the entrance and exit rate are solved by multiplying their concentration and its flow rate. So we also need to remember that the concentration of the rate of exit is dependent to the rate of entrance. It's because the concentration of the input rate gets mixed with the substance inside the container before it's going out. So that's why the concentration of the rate of exit is dependent to the rate of entrance. So now, we were going to solve some sample problems.
The tank contains 200 liters of fluid in which 30 grams of salt are dissolved. Brine containing 1 gram of salt per liter is then pumped into the tank at the rate of 4 liters per minute, and the solution mixed well is pumped out of the same rate. A. Find the number of grams of salt in the tank at any time in minutes. B. Find the amount of salt in the tank after 5 minutes.
Okay, so based on the given problem now, is we have here a tank that contains 200 liters of fluid in which 30 grams of salt are dissolved. And also, there is a solution coming inside the tank, wherein we have 1 gram of salt per liter, and that's the concentration coming inside the tank. And we have a rate of 4 liters per minute, so it's coming inside at a rate of 4 liters per minute now. And the solution is mixed well, is pumped out of the same rate. So meaning, the value of our R sub O here is equal to the value of our R sub I here, because it said that it's pumped out the puno at the same rate. And as you can see here, the C sub O is not given. So how do we find the C sub O? So the C sub O, just like what I said a while ago, no, it is usually expressed as x over v, x over v. So our formula here to use is v and this. So this formula are going to use later on. So first we need to find the value of final volume. So our V is equals to initial volume which is given 200 liter plus R sub I minus R sub O times T. So 4 minus 4 multiplied by any time T is we know that this would be equal to 0. So the final volume is would now be equal to the initial volume because of this, diba? So we will now, so we have final volume is equals to 200 liter because the value of our initial volume is 200. So therefore, our final volume is also 200. So if we are going to substitute it into our equation, we have T sub O is equals to X over 200 liters. So X still B, that is still X because that's the amount of salt at any time T. So we were going to substitute it into our equation here now. So we have dx over dt equals 4 times 1 plus 4 times x over 200, not 2000, sorry. So this is our differential equation na. And again, we can simplify this 4x over 200. We have dx over dt is equals to 4 minus x over 50. And if we are going to solve for this, we have 200 minus x all over 50. And applying the cross multiply, we have 50 dx over dt is equal to 200 minus x. So as you can see here, we are forming an equation that is linear of x. So let me just multiply both sides of the equation by -1. So I will be having a positive x na no after multiplying both sides by -1. So this negative 50 dx is equals to x minus 200 dt. And by variable separable, we have dx over x minus 200 is equals to dt over negative 50. So x minus 200 is at to siyang divide both sides. And negative 50 divides, so we have this na equation. Then now we can integrating both sides na because it's already separate. So the integral of dx over x minus 200 is equals to the integral of dt over negative 50. So what will happen na? In this, we have to let u dx minus 200 no? So therefore, let u x minus 200. So by integrate it kanang differentiate, we will get du is equals to dx because the derivative of 200, which is constant, is equals to 0. So du is equals to dx. So this is simply du over u. So the integral of du over u is equals to -1 over 50. We can factor out here the -1 over 50, leaving behind inside the integral dt. Now I'm going to integrate this na. So d over u is simply L in u is equals to -1 over 50 t because the integral of dt is simply t. And plus c. Don't forget the plus c. And this is not already the answer, no? Because, or yeah, the answer of this integrating because the value of u is x minus 200. So ln x minus 200 is equals to negative t over 50 plus c. So we have finished integrating na. So what do we need to find? So let's see the problem. In problem A, find the amount of gram of a salt in the tank at any time t. So we are here actually solving the value of x. Find the amount of gram of salt. So remember our x here is the amount of salt, right? So by solving the value of x, we must isolate the x, right? Then in this case, we must exponentiate both sides of the equation. So we have e to the power of ln x minus 200 is equals to e to the power of negative t over 50 plus c. Alright, so we know very well that the ln or the natural logarithm would actually be cancelled here, right? And by applying the law of exponent, we have e to the power of negative t over 50 multiplied by e to the power of c. Because if we are going to combine this, we will get this, diba? So we ano to, basta. But we know that the power of c, the power of e to the power of c is simply c or constant because e to the power of arbitrary is constant is constant. So we have x minus 200 is equal to ce to the power of negative t over 50. And by transposing the negative 200 on the other side, we have x is equal to ce to the power of negative t over 50 plus 200. And now, in order to find the amount of salt at any time t, we must solve for the value of this given constant, right? So using our initial condition, a while ago, this condition, at t is equal to 0 daw kuno, our x or the amount of salt inside the tank is 30 grams. So substitute this given value to this equation, we have 30 is equal to ce to the power of negative 0 over 50 plus 200. And our we know that a to the power of 0 or any number or any value to the power of 0 is equal to 1. So 30 is equal to c plus 200. So c is equals to negative 170 na because 30 minus 200 is negative 170. So our equation na for the amount of salt that anytime t is given na. So by simply substitute the value of c here, we have now, plug in na. So in any value of time here, in minutes, we can solve the amount of salt at any time t. So the value of c is negative 170. So x is equal to negative 170 e to the power of negative t over 50 plus 200. So our x is equal to 200 minus 170 e to the power of negative t over 50. Now, if we are plugging any value of any time t here in minutes, we can solve the amount of salt at any time t given, okay? Because this is the amount of salt at any time t. If we are plugged in any value of time here, we can solve the amount of salt. So let's solve the value of the problem B or the problem letter B. So the B daw kuno, the questions of B is find the amount of salt in the tank after 5 minutes. So at time daw kuno is equals to 5 minutes. So we simply substitute the value 5 here. So x is equals to 200 minus 170 e to the power of negative 5, which is our time in minutes, over 50. And if we substitute this into our calculator, we will be getting an answer of 46.18 grams. Okay, so that is how we solve our problems of mixtures. No, first is we need to identify the given, which is our C sub I, the concentration of substance at the entrance, and our R sub I, the volumetric flow rate at the entrance, and our R sub O, the volumetric flow rate gihapon at the exit na, and our C sub O. And always remember that our C sub O here is usually not given. So that's why we express this as X over V, which is our X here is the amount of solution solved at any time t, and our volume here is the final volume of the solution at any time t. So we can solve the final volume by using this formula, no? V is equals to initial volume plus the R sub I minus R sub O at any time t. So after solving the final volume, we can substitute here na. Then after, we can use na for this formula. dx over dt is equals to r sub I times c sub I minus our r sub o times c sub o na, no? Then, upon solving this equation or problem, we need to separate some variables using some cases, no? Like homogeneous, there are different cases that we can use to integrate, no? So that is how we solve the problem. So let's try other examples.
A tank holds 100 gallons of brine solution containing 20 pounds of salt. At T is equals to 0, fresh water is poured into the tank at the rate of 5 gallons per minute, and while perfectly mixed, leaves the tank at the same rate. So find the amount of salt in the tank of any time T. So now let's consider the given conditions. A tank which holds a 100 gallons of solution then contains 20 pounds of salt, where 5 gallons of pure water, which means that there is 0 amount of salt in the concentration, are added every minute, and then while perfectly mixed, leaves at the tank at the same rate of 5 gallons per minute. Now let's put a representation of the constantly changing concentration of our output rate. So x over 100 gallon. So here let's use variable x for the salt and divide it by the volume 100 gallon, which remains constant at any time since the flow rate of both input and output rate is just the same. So we also know that the original amount of the salt inside the container is 20 pounds. First, we write down the formula. So dx over dt is equals to r sub 1 times c sub 1 minus r sub 0 times c sub 0. Now, let's substitute what we found out earlier. So r sub 1 is equals to 5, then c sub 1 is equals to 0, minus r sub 0 is equals to 5 gallon per minute, times the c sub 0 is equals to x over 100. So, manipulating it further, we have dx over dt is equals to negative x over 20. Writing down below and manipulate it further, we will have dx over x is equals to negative dt over 20. So, the next step is to integrate both sides. Integrating this, we will have ln x is equals to negative t over 20 plus c. To eliminate our ln, we use one of the laws of logarithmic where e raised to ln a is equals to a. So let's raise both sides as the exponent of e, and then we manipulate the equation and then arrive in the form of x is equals to ce raised to t over 20. Now, this is our general solution. But what's asked in the problem is the amount of salt in the tank at any time t. This means that we need to come up with a function. Well, we could find the amount of salt in the tank at any given time. So, since we already know from the problem that t is equals to 0 and there was 20 pounds of salt, we can use this to find the value for c. We just have to use our general equation or general solution and substitute 20 for x and 0 for t. By manipulating this further, we'll find our c being equal to 20. Then going back to our general equation, we substitute 20 for c and finally arrive with an answer which is x is equals to 20e raised to t over 20. So this is our answer to our second and last problem.
Mastering differential equations empowers you to tackle real-world challenges.
Unlock insights, drive innovation,
And share the future with
differential equations.
real-world or Perez.